probably say, don't say enough. Anyway. So it's kind of because, like Correa and I both we don't have accents, so we don't look like we're a foreigner. We don't have these weird foreign things that, visiting cousins or whatever it is, or we don't like hugs. We can't handle hugs too much. Not that we don't like them, we just. What was the third thing? Do you know what the third thing was? Oh, it was about, well, I don't know if it was a cultural thing. It was because the date he went out on, and the girl was doing all these selfies and calling her how do you pronounce that?
Bae.
Bae, yeah. Yeah, Bae. This is me and my Bae. Yeah, the guy that she's just out with for one night, and he's this cameraman or something like that. I thought that was funny. Okay. So the last section of chapter 10 is something we've already talked about. So I'm just going to kind of go through here and skip over all that stuff. I think we may have already talked about this anyway. So remember, there's the Taylor series and there's the McLaren series, and there is one of these on the test. And so I'll give you a function, and you have to generate the Taylor series. You won't have to come up with the formula, because that takes. I might give you extra credit if you can come up with the formula. What I'm looking for is for you to come up with the first so many terms of the series, and then put little dots to show that it's an infinite series. So here's an example of deriving it for the natural log of x. Just let me cover this up here so we don't go too fast ahead. So the function is the natural log of x. We want to center it around x equals 1. And so we can evaluate the function at x equals 1, which is the natural log of 1, which is 0. So that's f of 1 is 0. And then you can take the first derivative, which the derivative of the natural log of x is 1 over x. So evaluating the first derivative at x equals 1, you get 1 over 1, which is 1. And what we're using these for is these are the coefficients that go in front of the various power terms that involve the power and the factorials. So and when you're taking the derivatives of something like this, you want to rewrite it as x to the minus 1 power at this point, because as you take subsequent derivatives, you're using the power rule with a negative exponent. So if I take the derivative of this, I'll have negative 1, which there's the negative sign, and then I'll subtract 1 from the exponent, which makes negative 2. So if I rewrite it as a normal rational number, I'll get negative 1 over x squared. And if you plug in 1 into that expression, you'll get negative 1 over 1 squared, which is negative 1. Now, the third derivative is going to be, you take negative 2 times negative 1, gives you positive 2. You'll get x to the minus 3 power, which is 1 over x cubed. If you plug 1 in there, you'll get 2. Now, I put it down as 2 factorial, because you'll see what happens as you go through here. You will, when you take the next derivative, you'll have x to the minus 3 power when you move this to the numerator. So you'll have negative 3 times, when you take the derivative, you'll have negative 3 times 2, which is negative 6, and then you get the next term. So, at this point, you could actually probably not even, you can see the pattern that emerges when you have this situation. So you take 4 times 6, but the negative sign would change to positive, so you'd have 24 over x to the 5th, and the next derivative would be 5 times 24, which is 120. You get a negative sign over x to the 5th. So if you keep evaluating these subsequent derivatives at x equals 1, you'll end up, the next term will be positive 4 factorial, and the next term which is the sixth derivative, will be negative 5 factorial. So those are the coefficients, which then you plug into the expression. So let me write the expression out again. So what it says is for a Taylor polyp series, you take f of 0, or not f of 0, f of c, whatever c is. So you take f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared over 2 factorial plus f triple prime of c times x minus c cubed over 3 factorial. We'll keep doing that. So that's the Taylor series, and you just keep doing that, and then I'm going to stop here in a second. And then you go to something, some equation, which sometimes you can deduce. Well, you can deduce, but I'm not, like I said, I'm not going to ask. I'm going to give you extra credit if you do that. So now all we have to do is plug in the values that we've got in the previous steps. So f of c is 0 plus f prime of c, which is 1, times x minus c is 1. We're centering the series around x equals 1. The next number here, this one here, is the second derivative evaluated at x equals 1, which is negative 1. So I have negative 1 times x minus 1 squared over 2 factorial. And then we have 2 factorial plus 2 factorial times x minus 1 cubed over 3 factorial plus 3 factorial times x minus 1 to the 4th over 4 factorial. Like that. And what you can do is, this 1 is 1 factorial, and 1 is also 0 factorial. So what I did there is I'm just putting those in there so that we can come up with the equation. So I had 1, the coefficient was 1, but 1 is also 0 factorial. And because I have 1 again, I have 1 factorial, which is 1. And then I have 2 factorial and 3 factorial. So this looks like n factorial, or n minus 1 factorial. This would be n minus 2 factorial, n minus 3 factorial if the exponent is n, and the exponent, well, actually we can actually simplify it beyond that, I think. Yeah, you could do it that way, or another way of simplifying it would be to have, you'd have x minus 1 divided by 1 minus x minus 1 squared divided by 2 plus x minus 1 cubed divided by 3. And that's because here we have 3 factorial in the denominator and 2 factorial in the numerator. So 3 factorial is 3 times 2 factorial. So if I rewrite this as 3 times 2 factorial and cancel out the factorials, and you could do the same thing here. 4 factorial would be 4 times 3 factorial. Cancel those out. So you just end up dividing by n. So as a consequence, let's see if I can figure out what the series is. Summation from n equals 1 to infinity of x minus 1 to the n power divided by n, and you have negative 1 to the, so when n equals 1, which is this one, we want it to be positive, so we'll probably put n plus 1. That way, by putting n plus 1 there, I get the correct alternating sign. I think that works out. Let's just try it. Let's try for n equals 2. So for n equals 2, that would be this situation. And I'd have negative 1 to the 2 plus 1 power times x minus 1 squared divided by 2. And negative 1 to the odd power is a negative, so it would be negative x minus 1 squared over 2. So that works. So I think that's right as far as the answer. And it's probably in your book. If you look on that sheet, you look at the series expansion for the natural log of x. It would be in section 9, 10, I think. Maybe, or is it 9, 10? So, yeah, that's what you get. So you'll see, and let's see if they gave the same answer. Well, the only difference is they did negative 1 to the n minus 1, which essentially gives you the same result. I did n plus 1, they did n minus 1. You just have to make sure that the negative sign occurs on the correct term. Okay, so that's a Taylor series. And they also talk about the binomial series. I didn't look at the interval of convergence for this. Should I do that? Yeah, maybe I will, because you have to do that with the test for some particular function. So let's go ahead and do that. Before we do the binomial series, let's just do another. Let's find the convergence for this particular series, which according to the book is going to be from 0 to 2, but not including 0. So what we would do is we would say that u sub n is negative 1 to the n times x minus 1 to the n plus 1. Did I do it right? Oh, this is from, yeah. Let me write the one I just did a minute ago. This was from me doing it in another year. So that was equal to the summation from n equals 1 to infinity. So we'll use the one that I came up with, which was n plus 1 times x minus 1 to the n over n. Okay, so let's ignore that. And let's add a page. Okay, so in this case, the way I came out with it this time, u sub n is equal to negative 1 to the n plus 1 times x minus 1 to the n over n. U sub n plus 1 is going to be negative 1 to the n plus 1 plus 1 times x minus 1 to the n plus 1 over n plus 1. So the convergence criteria is we look at the limit as n goes to infinity of the ratio of u sub n plus 1 over u sub n. So that is equal to the limit as n goes to infinity of negative 1 to the n plus 2 times x minus 1 to the n plus 1 divided by n plus 1 divided by, so that's u sub n plus 1, and I added the two ones together there. And then you get negative 1 to the n plus 1 times x minus 1 to the n divided by n. So that's u sub n. And that has to be less than 1. Again, this is the ratio test. So we take that and we group the terms that are similar. So we take the reciprocal of the denominator and then multiply it by the numerator. The way I've been doing it now that I'm doing this more, maybe, is I'll take these terms first, and then I'll match them up with the ones that are below, and they always create a ratio. So these are in the numerator. So negative 1 to the n plus 1 is in the numerator here. So this one has to be in the denominator. Then you've got this term, which is going to be x minus 1 to the n plus 1. That's in the top part. So the bottom part is going to be x minus 1 to the n. And this one is in the denominator, so I'll write that down first. So address each term in the original expression and put it in where it would normally be, and then the other part in the other one goes the opposite way. So I skipped the step of taking the reciprocal and then multiplying it. Just it always does that. So then you simplify. So what happens here is you just get negative 1 to the first power. Here we get x minus 1 to the first power. So we have n plus 1, we subtract n, we get 1. And the last term doesn't change. And now we can take the limit. Well, the negative sign here in the ratio test doesn't come into play. So really don't have to worry about that, because you take the absolute value of negative 1, you get positive 1. And also this ratio, n over n plus 1, this goes to 1. So basically the first term becomes 1 because it becomes positive. This is the absolute value part. So the absolute value makes this 1. This doesn't involve n, so it just stays the same, x minus 1. And the last term, as n goes to infinity, it becomes 1. And that has to be less than 1. So those are just simplifications as well as taking this limit. So using the absolute value and taking the limit gives you this. So what that says is that ultimately x minus 1 has to be less than 1. You add 1 to both sides. Well, it's the absolute value of this thing, sorry. So there's got to be absolute values in there. So with the absolute value like that, you can make it into this kind of inequality. And then you can add 1 to all parts of the inequality, and you get that, which is what we expected based on the book. So that's my interval of convergence. And it also makes sense because the series are always centered around whatever x value you center the series around. So we centered natural log around x equals 1. So that makes sense that the 1 is halfway between 0 and 2. And then you have to test the endpoints. And you'll have to do that on the test, of course. So the endpoints are, we're going to check at x equals 0, and we'll check at x equals 2. And the series that we're checking it with is the summation from n equals 1 to infinity of negative 1 to the n plus 1 times x minus 1 to the n over n. So when you plug in x equals 0 into here, you get negative 1 to the n plus 1 times 0 minus 1 to the n over n. So when this argument, this happens a lot, you end up with the positive number or a negative number associated with the center of this. So this goes to 0 when x equals 1. That's the center of the interval of a convergence. In this case, it's pretty simple because there's just negative 1. So you get negative 1 to the n plus 1 times negative 1 to the n divided by n. And then you combine the two with the same base. So they have the same base, so you add the exponents. So you'll have negative 1 to the 2n plus 1 divided by n. Well, this is always odd. And if it's always odd, then this is going to just become negative 1. So I can simplify it down there. So you get negative 1 over n. And we've done this many times. This diverges because it is a p-series, p equal to 1, which is less than or equal to 1. Okay, if P is less than or equal to 1, then the P series diverges. So this diverges, and therefore the series does not converge at 0. It diverges at 0, so we're not going to put an equals sign there. Now if you go to the other side, when x equals 2, you have 2 minus 1 to the n power over n. So then you get 1 to the n, and 1 to the n is just 1. So I'll write that out. So you'll get 1 to the n. So when you simplify this thing down, you'll have negative 1 to the n plus 1 times 1 over n. So that is an alternating series. And the convergence criteria for an alternating series is that the limit of a sub n as n goes to infinity equals 0, which is true. So that's true. And the second one is that a sub n plus 1 is always less than a sub n. And you can do that by putting in 1 over n plus 1 is less than 1 over n. If you cross multiply, you'll get n is less than n plus 1, or 0 is greater than 1, which is also always true. So for this case, it converges. It converges because of the alternating series. And so you get that one's equal to. So that's the final interval of convergence. So it converges on one side, it doesn't converge on the other. So make sure you understand that, because it's going to show up on the test. Okay. I'll give you a hint. It's not this problem, but it's a problem that'll end up having, it won't be all real numbers. It'll be a situation where you have values of x where it converges and where it doesn't converge. And one side will converge once you get the endpoints. One endpoint will converge and the other will not converge. And it will be because of this kind of relationship. It may not be the same side. It may be one side versus the other. But I will tell you that much, that one side will converge. And one side will converge because it's an alternating series, and the other side will not converge because it's a p-series. And I'm not giving away a lot because that just happens a lot. Anytime your initial series is an alternating series like this, a lot of times you do end up with one side converging and the other side not converging. So, okay, so there's... I just realized I haven't been wearing headphones. So, luckily, it still was on, so I'll just boost the sound up. Okay, the last one listed in your book for infinite series is the binomial series, where you have 1 plus x to the k power. And so you've seen that before. I mean, we're talking about k can be any value except, I think, 0. You probably put a little asterisk there somewhere or another. That's interesting. Yeah. So if you look at the book, your handout, it has a little asterisk and it says the convergence at x plus or minus 1 depends upon the value of k. So that must mean that sometimes it converges at the endpoints. It converges at the endpoints, sometimes it doesn't. So you can't generalize. But what we're talking about is something like x plus 1 squared. That's going to be 1 plus 2x plus x squared. And I don't know what happens if you make I mean, we know what the exact answer is here. You can kind of see, maybe after you get to this point, these drop out. I don't know if that's true or not. I hadn't thought about this before. Let's see what happens. I'm just going to try this, plug it into the formula. So you have 1 plus k, which is 2, times x, plus, then you have k, which is 2 times 2 minus 1 times x squared over 2 factorial. That cancels out with that. That's 1. So the first three terms of the series representation of a binomial series, for this case, is the exact series. What happens when you get the next value? You'd have 2 times 2 minus 1 times 2 minus 2 times x cubed over 3 factorial. And this is 0, so that whole term goes to 0. So that's what we hoped. And I guess that's what happens. That's kind of cool. I hadn't thought about that before. So you can see this this binomial, the series expansion. If you're looking at lower values of k, the ones we know the answer for, it gives you finite answers for the first n terms, and then the subsequent terms in the series, there's always one where it makes that term go to 0. So all the additional terms go to 0. So it does match up exactly for the ones that we're talking about. So where is this useful, right? You might say, well, it would be useful if k was something other than an integer. So how do you approximate, how do you come up with an answer for 1 plus x to the 1.2 power? You can't expand that out like that. So you couldn't do it in that form. And I vaguely remember in engineering there are cases where you end up with these situations, and what they do is they take like the first two terms, they say they take the first two terms of the binomial series to approximate this. So if I wanted to approximate 1 plus x to the 1.2 power, all I have to do is take 1 plus 1.2 times x and neglect the higher order terms. And if you're very close to where close to 0, then it's going to be pretty accurate. Let's just try that. So let's say we had 1 plus 0.1 to the 1.2 power. That's approximately equal to 1 plus 1.2 times 0.1. And let's ignore the higher order terms. See how close that is. But yeah, it's funny how your memory works. So that's the difference. So if you actually take 1.1 to the 1.2 power, you get 1.121. I don't think it's exactly 1.2121. It's got more decimal points. If you use the first two terms of the series representation of the binomial, you get 1.120. So that's pretty close. And it's kind of funny because I remember thinking now, this must be 35 years ago, you'd go to take these engineering classes, and probably even the advanced engineering classes, your PhD program, and I remember them saying, oh yeah, let's use the first two terms of the binomial. They would use this, and I had no idea what they were talking about. I just said, okay, yeah, that sounds good. So now I know. So that's I learned something new today, or I remembered something. Now I'm trying to remember what this one's all about. Oh, okay, yeah. So here's an example of, this may not look like a binomial series, but if you rewrite it as 1 plus x to the minus 2 power, you can have this formula applies for negative exponents. It also applies for non-integer exponents. And the advantage here clearly is that this, if I were to look at this expression, I have 1 over x squared plus 2x plus 1. This is a rational function, whereas if I use the series expansion, it's now a polynomial. And so sometimes polynomials are easier to deal with in doing analyses than dealing with rational functions. So it allows you to get rid of a rational function. So all I've done here, problem 15, is I've set k equal to negative 2. So you get, if you look at the, let me pull the formula forward here, show how you use it when k is negative. So here's the formula. So the first term is 1 plus k, which is negative 2 times x. Then you have k, which is negative 2 times negative 2 minus 1, which is negative 3, divided by 2 factorial. Then the next term, this term here, you have negative 2 minus 1 is negative 3, minus 1 is negative 4, times x cubed over 3 factorial. And then the next term, you have that. And what you can see is that this, well, I was going to say it alternates. I think I made a mistake here. This should be plus. So when you have the rational expression, every other term is a different sign. And that's because every time you add one more negative, here we have 4 negatives, so we get a positive number. Here we have 3 negatives, so we get a negative number. Here we have 2 negatives, so we get a positive number. And so if this, and I apparently have done something wrong because it's not working out here. So let me fix that. So this one's positive, negative, that one, this must be negative. I don't know how I got that wrong earlier. So that's negative, positive. Okay, so that's all we're saying about the binomial series. But if you do take engineering, you might actually hear that again. Now I'm curious. I have to go back and look in some of my textbooks and find out where they use that particular approximation to simplify things where you had a fractional or a decimal exponent. I'm trying to think where that might have been. Okay, and the last topic is just using the table of elementary functions, which you have as a handout, this one here, how you use this to come up with a series of representations of more complex expressions. So instead of going through the whole process of doing a Taylor series or a Maclaurin series on this, what we can do is we can use the fact that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so forth and so on. So if you do e to the x squared over 2, it's just going to be 1 plus x squared over 2 plus x squared over 2 squared over 2 factorial plus x squared over 2 cubed over 3 factorial. And you could simplify that down to 1 plus x squared over 2 plus x, why am I squaring it? Oh yeah, x to the 4th, x to the 4th over 2 squared times
2 factorial, and then you'd have x to the 6th over 2 cubed times 3 factorial. And you could probably come up with an expression. Let's try to see if we can figure this out. Summation from n equals 0 to infinity of x to the 2n divided by 2 to the n times n factorial. So I think that works out, because if you have n equals 0, you'll get x to the 0, which is 1. 2 to the 0 is 1. 0 factorial is 1. So all of these, at n equals 0, all the terms are 1. When you have n equals 1, you'd have 2 times 1, so you'd have x squared divided by 2 to the first power, which is 2, times 1 factorial, which is 1. And then if you let n equal 2, you'd have x to the 4th over 4, or 2 squared, times 2 factorial. So that would be the result. Okay, let's look at another one. Okay, so you got the cosine of 4x. So we know that the cosine of x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. So all we have to do the cosine of 4x is going to be 1 minus 4x squared over 2 factorial minus 4x to the 4th over 4 factorial minus 4x to the 6th over 6 factorial. We already talked about this one, the hyperbolic sine, and we talked about that already. Did I go too fast for you here? I'll leave that up for a second. I think most of the ones that I have shown still we've already talked about to some extent. Actually, while I'm thinking about it, I saw this as an example in the book. Let's say if you wanted to find what the integral of x e to the x squared dx. We already know how we would use integration. Well, in this case, we would just use a u substitution. So, where you would let u equal x squared and du would be equal to 2x dx. So you could do this one. We know how to do that one using u substitution. If I had x times e to the x dx, we would use integration by parts, where u equals x and dv equals e to the x dx. How about e to the x squared dx? How do you do that one? Well, we can't use integration by parts because there's no multiplication. So, and the derivative of the exponent is not there, like the first case was. Well, this would be a case where you could use the series. You could come up with a series solution. So the first thing that you would do is you would, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Therefore, e to the x squared is going to be 1 plus x squared plus x squared squared over 2 factorial plus x cubed squared, x squared cubed, sorry, x squared cubed over 3 factorial. And therefore, the integral of e to the x squared dx is the same as the integral of 1 plus x squared plus x to the fourth over 2 factorial plus x to the 6 over 3 factorial, and it would have an infinite number of terms, dx. And then all you have to do is do the polynomial integration. So you get x plus x cubed over 3 not 3 factorial, just x cubed over 3 plus x to the fifth over 5 times 2 factorial plus x to the seventh over 7 times 3 factorial. And you could then probably come up with an equation, some summation of something here. Let's see if we can figure out what it is. X to the 2n plus 1, start at n equals 0. So what that does is when n equals 0, I'll have x to the first power. When I have n equal 1, I'll have x cubed. And then I divide by 2n plus 1, because those match up. And then I would divide by n. This is q. This is n is 3, so n factorial. I think that would be it. So when you have n equals 0, you get 0 factorial, which is 1. This is 1. You get x to the first power. So that works. When n equals 1, you'd get x cubed over 3 times 1 factorial, which is what we get there. So that looks like it. So that's a way to come up with a solution, an analytical solution. Even though it requires an infinite number of terms, it's still an analytical solution. As long as you take enough terms, you'll come up with the exact, or close enough to the exact answer. Okay, so there's the homework for this section. I think, yeah, we already talked about how you get e to the I theta equals cosine theta plus I sine theta. So I think pretty much covered everything that we need to. I might come back, not today, but before the test, I might do one more of those geometric series type things that we did yesterday, because that is on the test, and I want to make sure that I want to make sure that you know how to do that kind of problem. Okay, that's all. Staying here for well, yeah, we'll be here for physics.